Morning, everyone. My name is Tessa Baker. It's a pleasure to be invited to speak at the 40th anniversary of MOND, so happy birthday, MOND. So I was invited to give you something of an overview of how we go about testing gravity and deviations from GR in cosmology. And I've called this twin tests of gravity because, as we'll see, there'll be two sort of main camps of tests I'll talk about today, which will be gravitational waves and large-scale structure. So just to orient ourselves a little bit, here is a plot I made together with Cosmological, who was here earlier in the week, some years ago now. And this was an attempt to sort of display visually all the different gravitational regimes we could think to test. So we came up with a set of axes, and I should stress, these aren't sort of uniquely defined. There'll be multiple ways of doing this. But the axes we chose were gravitational potential, so just good old familiar Newtonian potential. And we came up with a quantity that assesses space-time curvature of the metric. Okay, and I won't go into the technical details today, really, because we just want to look at the plot, but they are in that reference. And then we started putting systems on these two axes. So there's a lot of acronyms here. These 8 blue points here, labeled SS, those are the planets of the solar system. And they're all lying on a straight line because they're all, of course, probing mainly the gravitational potential well of the sun. Moving on up to slightly higher curvatures, we've got pulsars. MS is representing main sequence stars. WD is white dwarfs. And then over here in the very top right-hand corner, high curvature, high potentials, we have the strong field regime near the surfaces of neutron stars and black holes. The S stars orbiting around the center of the Milky Way are sitting here. And then moving downwards towards the lower curvature regimes, we have a set of rotation curves just representing the approximate area of galaxies, and also some cluster profiles. And then right down the bottom, in the ultra-low curvature regime, we have cosmology, large-scale structure. So this thing labeled P of K is meant to be the matter power spectrum. Those questions, okay. Okay, so that's our kind of spread of systems. Now, on these axes, an acceleration scale corresponds to a diagonal line, sort of slanting like this. And so, of course, we put on this plot a very familiar acceleration scale, around 10 to the minus 10 meters per second squared. Okay, and you can see that slices directly through the regime of galaxies and clusters. So in some sense, this is kind of the visual representation of where the MOND regime is, at least on these axes. And of course, we see that cosmology is below this at very low accelerations. Okay, and this plot is a little bit unfair to cosmology because it really sort of squashes all of cosmology into the bottom corner here. But this is the regime that I am going to be talking about today. Okay, testing gravity in this cosmological regime. Now, I should say, this is not a talk specifically about MOND. My work is about connecting the latest developments in gravity theory with the latest exciting data in cosmology. And I try and do that in a manner that's as model independent as possible. Okay, and we'll see in a few minutes how model independent one can actually be. But in some sense, what I'm going to do today is give you a sort of whistle-stop tour of some of the most exciting developments and bits of data that I think about, and I leave it up to my discerning audience to decide whether they would like to apply those same observations to other theories of interest. Okay, so we'll do this in 3 sections today. I'll start off by introducing the particular framework that I am going to use to assemble these tests of gravity. Then we'll talk about the bounds on those parameters from the gravitational wave side of things. And then we'll talk about the bounds coming from the large-scale structure side of things. And I should say that a lot of the things I'm going to tell you about today, at least the parts that are my own work, are driven forward by my fantastic team of PhD and postdocs at Queen Mary. So here they all are, and credit to them. Okay, so let me get started by setting up the framework that I am going to use to talk about these tests of gravity today. So, going around and testing individual theories of gravity can be quite an inefficient process, right? There's lots and lots of ideas out there in the theoretical literature. And so rather than testing them individually, a sensible strategy would be to try and map that theory landscape onto a parameterization, right? A smaller set of numbers that you can then try and constrain with your data. And of course, we have an example of this in the parameterized post-Newtonian formalism, PPN. And what we would really like is something akin to that, but that can be applied to cosmology. Okay, so here's the idea. Visually, you have your large theory space. It's got theories you know about and you've worked out and published on arXiv, but it's probably also got patches you haven't even thought about yet. And you want to map that on to a smaller parameterization space, and then you come along with your observations. You find they prefer some patch of parameterization space, and I've deliberately made it some kind of weird shape. And of course, it's key that you can reverse that mapping to understand what is the patch of parameterization space, what does that correspond to in your theory space. Okay, and if you're lucky, it corresponds to a theory you know about. Maybe it corresponds to some part of theory space you've never even thought about. Okay, and that's important for driving forward development of new ideas, right? This is the interplay between theory and data. So I spent a large part of my early career trying to figure out how to build these parameterizations for models of modified gravity and dark energy. And rather depressingly, I can now summarize my entire PhD thesis in one sentence, which is that there's no 100% perfect way to do this. But what you can do is build these parameterizations for families of theories that have particular field contents. Okay, so I can't give you one set of numbers that will cover every idea in gravity, but there is at least a sort of a mathematically well-defined process you can go through to parameterize theories that have, say, the metric of GR plus extra scalar degrees of freedom, or the metric of GR plus new vectors, or if you want to, throw in combinations of those things. Okay, so there's a set of parameters for each of those families. And again, I won't, to cover the ground today, I won't take you into the kind of technical details of how we build this, but it's also in this reference document. Okay, so what I'm going to do today is, of course, tackle the simplest possible family we can describe this way, which is Horndeski gravity. So essentially what's happened here is we've adopted a kind of effective field theory mindset. We've written down the most general Lagrangian we can that has a metric and an extra scalar degree of freedom and obeys some appropriate symmetries. And in the case of one extra scalar degree of freedom, this gets you to this theory called Horndeski that some of you may know. So there's a Lagrangian you can write down for this thing. I'm actually not going to write it down because it's about 5 or 6 lines long because of the operators. And this audience could handle it, no problem, I'm sure, but it's just not necessary for this part of the story. We might see a bit of it later. So let's just take it for now. There is some big, messy Lagrangian you can write down that contains our extra scalar field phi and our metric GVU. Okay, and I'll couple this to a matter Lagrangian. Now, of course, what we care about a lot in cosmology, at least our kind of first-order description beyond a smooth expanding universe, is to build a theory of linear cosmological perturbations. Right, this is the starting point for calculations of the CMB and of large-scale structure. So we want to derive linearized field equations from this big, messy Lagrangian. Okay, we can do that fairly straightforwardly. It's a turn the handle exercise. And what we will get out is a set of equations. So these are extensions of the corresponding field equations in lambda CDM. And you'll find that wherever there is a new term in these field equations, so something that's not present in GR, it is accompanied by a coefficient that depends on a set of 4 objects. So there are 4 of these objects. We label them alphas, and we call them the Horndeski alpha parameters. Now, this is a complete abuse of terminology. They're not constants, and so we shouldn't really call them parameters. Okay? As I've indicated on the slide, they are functions of redshift, because they're doing cosmology. But nevertheless, I will kind of keep up the abuse of terminology today and just call them the alpha parameters. Okay, so wherever there is a deviation from GR, it contains one of these 4 objects, or combinations of these 4 objects. And that means if we set all the alpha parameters to 0, we get back the linearized field equations of lambda CDM and GR. Another nice thing about these 4 Horndeski alpha parameters is that they have sort of semi-physical meanings. There are words you can drape around them that say what they're doing. So let's meet them. So alpha t describes the deviation of the speed of propagation of gravitational waves from the speed of light. Okay, so the speed of propagation of gravitational waves will be ct, t for tensor mode, and alpha is the deviation from 1, and I'll use natural units today. Alpha m describes the rate of evolution of the effective Planck mass. So a lot of theories of dark energy and modified gravity can give us what looks like a time-evolving gravitational coupling strength. Okay, time-evolving big G, and of course that's equivalent to a time-evolving effective Planck mass. And so that rate of change with redshift or time is described by alpha m. Alpha b is called the braiding parameter, and it describes the appearance of a particular interaction between the kinetic terms of the scalar field and the kinetic terms of the metric. And finally, we have alpha k, called the kineticity parameter, and this controls, or is related to the kinetic term of this scalar field itself. So do we have a very canonical scalar degree of freedom in our theory, or have we got something with a very exotic kinetic term? That can happen in some theories of dark energy, like K-essence and camouflage, those names. Okay, so those are our 4 parameters that describe linearized cosmology with an extra scalar degree of freedom. And what we want to do is set about constraining these with data. Right? And then one of 2 things happens. Either we'll find one of them is different from 0, and we've detected a deviation from lambda CDM, and we can probably go and collect a Nobel Prize for that. Or we constrain them all to be very close to 0 or exactly 0. And what that does is it then rules out that family of theories that have one extra scalar field. Okay, and that's useful. If we can shut doors on particular families of theories, again, that drives forward theoretical development. It tells us where to focus our attention. So that's still a good outcome. Okay, so that's the framework I'm going to use today. Let us proceed to talking about how we actually bound these things. And we're going to start off with the bounds from gravitational waves. And I should advertise that as we work down our list of constraining these 4 alphas, things are going to start nice and simple, and then it's going to get progressively more complicated, and then at the end of the day we're going to have to throw out the scheme altogether. But I'll explain that when we get there. Okay, gravitational waves. This is a topic which doesn't need a lot of introduction these days. I assume everyone, to some extent, has heard about the first detections of gravitational waves by the LIGO, Virgo, and CAGRA detectors. And just as a reminder, there are 3 kinds of sources that we have confirmed detection of to date. So by far the most numerous are the binary black holes. Okay, and from those we get just a pure gravitational wave signal. We also have 3 confirmed neutron star black hole mergers. So that's that one here. And from those we get the gravitational wave signal. And there maybe could be an electromagnetic signal, but we haven't seen one yet. So we're not sure if there's a chance for photons to actually escape in those mergers. And then, of course, the final system are binary neutron stars. And in this case, we know that there definitely can be electromagnetic counterparts, right? Because you're smashing together these 2 neutron stars. There's no event horizons, at least to start with, so it's a hugely energetic event, and photons can escape. Okay, and you may know that we have one event to date, only one, which is what we call a standard siren. So that is a binary neutron star merger for which we have detected gravitational waves and photons. And it is that one standard siren event where we start off with our constraints on our Horndeski alpha parameters. So this was the binary neutron star merger GW170817 in the call signs we give these things. And its counterpart is, its EM counterpart, was seen all across the electromagnetic spectrum. But the part we're interested in today is the gamma ray photons. So that's GRB 170817. And what you've got on the left here is the data from that event. So this middle plot here is called a spectrogram, and it shows the spread of frequencies in the gravitational wave detector as a function of time. So you can see the signal here. You can see it chirp up towards merger over a period of a couple of seconds. And then the top and bottom panels show flux counts in 2 gamma ray spectrographs that were operating at the time, Fermi and integral. And you can see, perhaps most clearly in Fermi, this bump, this peak in the gamma ray flux counts, and this was identified as the start of the EM counterpart. And the delay between the merger in the gravitational wave signal and the start of that counterpart is about 1.7 seconds. So the fact that we have these 2 signals, photons and gravitational waves, arriving at Earth within 2 seconds of one another allows us to place a bound on any relative difference between their speeds of propagation. Okay, and remember that was exactly what's parameterized by our first Horndeski alpha parameter, which was alpha t. So you can do this calculation. It's pretty straightforward, especially because this event was so nearby. So it's just a kind of time of flight calculation, more or less. And what you will find is that the bound on that alpha t parameter is about 10 to the minus 15. Okay, so gravitational waves seem to be traveling at the speed of light to within 1 part to 10 to the 50. That's a really, really tight bound. A couple of caveats. First of all, this is only one data point, right? So you can be sure if we have more of these events, we will definitely check this again. You don't kind of just claim a result with one data point alone. Secondly, this event is at low redshift. So in principle, with our one data point, we can't rule out the possibility that alpha t, which remember is actually a function of redshift, we can't rule out the possibility that it does something more exotic at high redshifts. I'm not saying I think it should do, but it's still an option. Sometimes people ask, what have you assumed about the actual emission of the gravitational wave of the photon? So this bound assumes that they are released exactly simultaneously, or rather that the gamma ray photon is released exactly at the time of merger. Now, astrophysically, merging neutron stars is a total mess, and so that doesn't have to be the case. There can be a delay of about 10 seconds between the merger and the first gamma ray photons being released. That would weaken this bound by an order of magnitude. Okay, but 10 to the minus 14 is still a really, really tiny number. So it's still a really tight bound. So this was the headline results back in 2017, and there was a sort of flurry of activity trying to understand what this implied for extensions of GR. And the headline claim at the time, at least in this Horndeski family of theories we've been talking about, is that it rules out the most complicated parts of the Horndeski Lagrangian. Okay, so the simpler parts which remain, and I will show these to you later. So there are still Horndeski families that survive, but some of the more exotic members of the family get ruled out. Actually, there is a little bit of a subtlety there, which I don't have time to talk about, but if I can seed you with an appropriate question for the end of the talk, that's a good thing to ask. Okay, and also what we learn is that gravitational waves and photons need to be propagating on geodesics of the same metric. So if you have a theory that's got some new effective metric in, you can't have gravitational waves and photons coupled differently to that. Otherwise you'd get a bigger difference. Okay, so more or less that's kind of the headline result for the speed of propagation. And that pretty much, up to the loopholes and the caveats that I've mentioned, that kind of constrains or rules out our first Horndeski parameter. That's the easiest one. So let's carry on, and let me tell you about the second parameter here, alpha m, which remember was the rate of the effective change in the Planck mass. How do we constrain that? We're sticking with gravitational waves for now. And to constrain this parameter, we talk about gravitational wave propagation. So here I have I'm trying to say expression and equation at the same time, which comes out as the expression. Here we have an expression for a gravitational wave propagating on an FRW background in GR. Okay, so our gravitational wave, our spin-2 perturbation of the metric, Hij, we know packed into that in appropriate gauge choices are the plus and cross polarization modes. And it's a wave equation. It's got a second order time derivative. It's got a second order spatial derivative. But importantly, it's a damped wave equation. It has a friction term in there. And the friction term depends on the Hubble factor. So the fact that our gravitational waves are traveling through an expanding universe has an effect on this friction that they experience. And really, what friction is going to do is it's going to damp the rate, it damps the amplitude of the gravitational waves as they travel. Okay. That's the situation in GR. What happens if instead our gravitational wave is propagating in our Horndeski family of theories? So we pick up two new factors in the equation. I've coloured them in. So the one over here we've spoken about already. That's the modified speed of propagation, CT. Okay, so that sits in here, but we've kind of done that. So I'll just set that to 1. What we now see is that modifying this friction term is our alpha m parameter, the effective change in the Planck mass, or in big G. And so intuitively, that's somehow going to get tangled up in the change of amplitude as the wave travels. So let's make that a little bit more concrete. Here is an expression for the amplitude of a gravitational wave in frequency space. And I've made all the simplifying assumptions. So I've assumed two black holes, non-spinning, circular orbit to lowest post-Newtonian order. Okay, so this is just part of a longer expression, really. And we can see it depends on the what we call the chirp mass, which is a particular combination of the two masses. There's a bunch of angular factors. And what we really care about today is this distance, which sits in the denominator, which is the luminosity distance. Okay, so it's one of our many distance measures we like to define in cosmology, and it's related to redshift by an expression shown here. And you'll note that this expression contains the Hubble factor. And this is actually the starting point for gravitational wave cosmology. The idea that we might be able to constrain the Hubble constant with gravitational waves and maybe solve the Hubble tension. That comes about if we have a system like a standard siren that allows us to measure both the luminosity distance on the left and we have a way of getting the redshift. Because if we can pin down both of those variables, we can basically access or constrain parameters that sit in here, like the Hubble constant. Okay, so just pointing out there's a whole other talk there, a whole other avenue I could give in which we go and talk about gravitational wave constraints of the Hubble constant. But today we'll stick with the tests of gravity. So what changes if we have our theories beyond GR? Well, what they will do, at least what these Horndeski theories will do, is they will change the effective distance that sits in the denominator here. Now, I say effective distance because they're not actually physically moving the gravitational wave sources around. They're just affecting this quantity that you interpret as a distance. So this is now a different distance. We very inventively call it the gravitational wave luminosity distance, dGW. And the statement is this is no longer equal to the normal luminosity distance, dl. And so people often talk about measuring this ratio. And if it's 1, we say, oh, that's consistent with GR. And if it's different from 1, we say, oh, that's a smoking gun for some deviation of GR. So you can solve the wave equation, and you can actually relate this ratio to our alpha m parameter. Okay, and you get some factor that contains exponentials and integrals and details that don't really matter today. Okay. So what we want to do, as with the Hubble constant measurement, is we want to find a way to measure the numerator here, which we can get from our gravitational wave signal. And we also need to get a redshift. And if we have a redshift, we can compute dl, just assuming FRW cosmology, and therefore we can infer the denominator here, and therefore we can constrain our alpha m parameter. Okay, straightforward. So we need redshifts. Well, we've only got one event so far that has a confirmed EM counterpart, and therefore a confirmed redshift, so let's try that. So what are the constraints from 1708-17, the standard siren? Well, here they are. So what you're seeing here is a posterior on this alpha m parameter. And actually, remember, that's a function of redshift. So really, we're just constraining its value at redshift 0 or close to 0. And there are two curves here because it depends on what you take as your prior on the Hubble constant. So there's a Planck version, and Shoes is part of the low redshift distance ladder Hubble constant measurements. Again, difference doesn't really matter today. The point is the scale of these things. So for 2 sigma, your constraints on alpha m are about plus or minus 100. And remember, we had for alpha t 10 to the minus 15. So this is a bit disappointing, to say the least. Right? It is not a tight constraint. Why is it doing so badly? Well, it's doing badly because 1708-17 was at very low redshifts. Right? It's basically in our cosmic backyard. And the way this ratio works, remember, it had an integral in it. So if the event's nearby, that integral has a very small range, and so the thing reduces to 1. What we would really like is to use events from higher redshifts, because these deviations, these changes to the friction, accumulate as the gravitational wave travels. So higher redshift means basically greater distance or greater time for those deviations to build up. And we do have gravitational wave events at higher redshifts. So this is a plot of the current catalogue of confirmed gravitational wave detections. 1708-17 is the event right in the corner down here. But you'll see we do have things going up in redshift to about redshift 1. Yeah, with large errors, that's true. But we do have things that we're pretty confident are at larger distances. So we want to use those. Problem, those are all binary black holes. They do not have EM counterparts. So how are we going to get a redshift? Well, I sort of gave the game away in the title of the slide. So there is a method that we've been developing called dark sirens, which attempts to solve exactly this problem. Okay, and this method is basically spelled out by this series of 3 pitches. conceptually at least. So what are we doing? So when we get a gravitational wave detection, one of the things that the detectors give us is a sky map. Okay, so it's a projection of the sky on a 2D plane, and it shows us where the detectors, in quotes, think the event has come from, based on their sensitivity and their antenna patterns. Okay, so you get some contours like this. Now this looks like a 2D piece of information, but actually there is a radial sensitivity in there. There is distance information. So we can project this into 3D. That's what's happening here. So you have to imagine the Earth is at the center there, and these sort of red lobes are marking out the localization volumes, the volumes of space where we think the source of the gravitational wave is. And of course we can go look at those volumes of space with a telescope, and what we'll see are thousands of host galaxies. Now if we're lucky, somebody has come along and done a galaxy redshift survey for us. And I apologise to any survey astronomers in the room because I know that's not a trivial thing, but we'll just assume that's been taken care of, and we have redshift measurements for all these galaxies. And then that means something interesting. It means you do actually have the true redshift of the gravitational wave source sitting somewhere on your hard drive, because it has to live inside one of these galaxies. The problem is you don't know which one. And the basic concept of this dark science method is that it will marginalize your constraints, whether that's on the Hubble parameter or your modified gravity parameter. It will marginalize that constraint over all the possible host galaxies within that localization volume. Now what that means is that you're going to get a very weak constraint, right? Because of all the possible redshifts. But the beauty of this method is that you can stack your data. You don't have to wait for these special standard sirens with EM counterparts. Every plain old vanilla binary black hole that comes through the detectors can be used. And so we can add all our weak data together, and we actually start getting something reasonably constrained. Okay, so this is what I've said. We substitute the EM counterpart with a catalogue of galaxies. And the downside is that this is a more costly analysis. I'm not going to take you into the hierarchical Bayesian formalism behind this today. We don't have time, but there is a full formalism behind this. But as I said, the pro is we use all our data, and we get to use our data from higher redshifts, which, as we've seen, are better suited to these tests of gravity. Okay, so I'm going to skip this slide. This is just a little bit more detail on how we actually do this. I will jump to the results, at least the current results. So this method, via lots of things I've had to leave out, can be used. And we can't just constrain one parameter. We can't just constrain our modified gravity parameter. It's degenerate with, first of all, the Hubble constant, and second of all, a bunch of parameters that describe the mass distribution of compact objects in the universe. So that's why I end up showing you these kind of big, ugly corner plots, is because we have to infer all these things together. But I've tried to highlight that this is the row you really care about. This is the modified gravity parameter. Now, the way this analysis was set up, and this was done by my student, Anson Chen, the parameter he's constraining is actually not exactly alpha n. It's something very similar. So that's why the label here does not say alpha m. But I'm going to ask you today to just think of this as the alpha n parameter. Okay, the only difference is that alpha m, which is what we were trying to constrain, is 0 in GR, and this other parameter that Anson's constraining is 1 in GR. But small differences, otherwise they do pretty much the same thing. And so this constraint comes from using 42 binary black holes in the current catalogue, which is GWTC3. And I don't know if you can see the labels here, but the current constraints on this parameter are about 4 plus or minus about 2.8, that says. So the current constraints are still a bit weak. Okay, they're better than 100. We're down to the kind of order unity. But it's still early days. And this is because we've only got 42 data points going in here. But this will change, right? The fourth observing run of LIGO has started. We're part of LIGO, so all our pipelines are ready to go on that data. So this is something that we hope to improve in the next couple of years when we have a few hundred more gravitational wavelengths. Okay, so order unity constraints. Hopefully I've outlined for you there is a pathway for this to improve. Okay, so we've done 2 alpha parameters in definitely 2/3 of the times. We constrained alpha t very strongly. Alpha m, I've sort of explained why there's weak constraints, but also that dark sirens offer a route to doing this in future. In my remaining time, I will try and tell you about the other 2 parameters here, alpha b and alpha k. And for these, we leave behind gravitational waves and we go to large-scale structure. Okay, so those 2 remaining parameters do not impact gravitational waves. But what they do impact is the large-scale structure of the universe. Okay, when we talk about large-scale structure, we talk about a division between linear and non-linear regimes. Okay, so this is a matter power spectrum, and I am assuming just standard dark matter today. And so we look at this in Fourier space, so large scales on the left, the regime that is well described by linear cosmological perturbation theory. And as we go towards smaller and smaller scales, we get into a regime where that perturbation theory breaks down, those density fluctuations are non-linear, and we can no longer calculate things by hand. We have to build numerical simulations to study how structure forms. This is also the regime where the frontier data is coming from. So our next generation galaxy surveys that are starting soon, Euclid, Vera Rubin, really the regime they're pushing into is this small scale regime. There's a couple of curves on this plot. So GR is in blue. The grey is just showing the prediction of linear theory, and you can see that breaks down. And then the pink is corresponding to a particular gravity model. In this case, it's f of r gravity. Doesn't really matter today. What I need you to see is that all of these things are very closely agreeing in the linear regime, and they are starting to deviate more strongly in the non-linear regime. Okay, so that's why this is an interesting place to go test for departures from GR. Now, here we get to a slight kind of subtlety, and this is why I have to kind of pull the rug out from under you a little bit. So I've been talking about these Horndeski alpha parameters, but remember I said those were the descriptors of linear cosmology. So they apply over here, and there are constraints on them in this regime. They're sort of order unity, effectively. But what I want to tell you about is the attempt to constrain things in this non-linear regime. And that means we have to give up on the Horndeski alphas. We're going to have to substitute them for a different set of objects. So we go back to the Horndeski Lagrangian. And this is what I didn't want to show you to start with, because I said it was big and ugly. But once I've applied the constraint on speed from 1708-17, I said that killed off a lot of the ugly terms, and what we're left with is a Lagrangian compact enough to fit on one line. So what have we got? We've got the Ricci scalar as per GR, but now it's being multiplied by some conformal factor, which we call G4, which depends on our scalar field. Okay, so if this is Planck mass squared over 2, we get back the Einstein-Hilbert Lagrangian. We've got some function I'll call K of our scalar field and its kinetic term, which we normally call X. And this is kind of the fancy generalization of a kinetic term. And then we've got a self-interaction term, so we've got a box phi, and again it's got a coefficient G3, which depends on phi and X again. So this is kind of where all the non-standard interactions of your theory come in. Okay, so what we now want to constrain really for the full theory is not the alpha parameters, but these 3 objects, G4, K, and G3. Okay, and again, they're functions. And these are kind of the grown-up versions of the alpha parameters, because they're the full descriptors of the theory. So we can use these in the nonlinear regime. Okay, I said this nonlinear regime requires simulations. We can't compute it analytically. So that means we need to build simulations for Horndeski. Fine. Problem, how do you build a numerical simulation for a whole family of gravity models? Okay, essentially all cosmological simulations to date either use lambda CDM, or the ones that have gone outside of lambda CDM, they've been hard-coded to a particular theory of gravity. Right? You have to code up what is the force between particles. So this is a problem that my team and I have been working on for a couple of years. And of course, I'm going to take the opportunity to advertise the fruits of our labor, which is a simulation suite called HiCola. And that stands for Horndeski in Cola, nested acronym. Cola itself stands for co-moving Lagrangian acceleration. It's just the name of a particular algorithm that's used in the code to make it quite fast. Okay, and HiCola is the first simulation code, at least as far as I'm aware, which is flexible with regards to its gravitational laws. So it is not hard-coded to a particular model of gravity. You, the user, come along, boot it up, and you put in the theory of gravity you want to simulate. Okay, I have a code diagram which is probably a little bit overcomplicated, particularly for this conference. But let me just point out the kind of key features of how this works. So you come along as the user, and you choose the functional form of those three objects, K, G3, G4, which were the descriptors of the Horndeski Lagrangian. So you're literally putting in a Lagrangian. There is a front end of the code which uses a lot of symbolic algebra to work out the field equations you need for the cosmological background, for the linear theory, and for the nonlinear part of the code. It then turns all of those into numerical routines on the fly, and it feeds them into the simulation itself, which then goes about doing its thing and actually moving particles and simulating structure with that theory of gravity that you just put in. Okay. So one of the nice things about building your own simulation code is you get to pull out nice pictures. And I should say that the code is publicly available. So here are just some snapshots from HiCola runs. So there's of course, this is a dark matter simulation, so here's our dark matter distribution. Because we follow particles through from early redshifts to redshift 0, we can trace them back. So we can look at dark matter halos, and we can even trace back where all the particles in that halo came from, what we call proto-halos. And yeah, here we go. Here's a little movie of the thing running, and it'll loop. So it starts out as a flat grey distribution. It's quite hard to see because it goes quite quickly. And you can see that uniform distribution collapsing into the filaments of large-scale structure. Okay, and you can't tell by eye whether that's lambda CDM or a modified gravity theory. But I could run lots of boxes with lots of different gravity theories and put them side by side. So the key output that we study is the power spectrum of this large-scale structure. That's one of the first places we would look for these deviations from GR. And what we usually do is we plot that power spectrum as a ratio to its lambda CDM prediction. So I've got a bunch of gravity models here in different colors. Don't have to worry about the specifics today. One, so lambda CDM is down here. And what you see is that there's some kind of very generic features that emerge in a lot of models. So there tends to be an enhancement of power at large scales, which is often kind of scale independent, so there are these flat areas. Then as we get towards smaller scales, we start getting this rise, so we're getting even more enhanced structure, and it's not scale independent anymore. And then at the very small scales, things start to drop off back towards lambda CDM again. And that's because the theories we're simulating here have a property called screening, which acts in very dense environments to push them back towards GR. Okay, so this is early days for this code, but from these outputs we start to get a handle on how large-scale structure varies in all these different theories of gravity, and the aim is ultimately to use these with the data from these stage 4 upcoming surveys to actually put constraints on these clandestine models. So that's a work in progress. I can't show you the final answers today, but let me kind of recap the final state of play of our alpha parameters. So this one, strongly constrained. This one, weakly constrained, or constraints order unity right now, but a clear path to constraining it with the next few years of gravitational waves. These two parameters, I said, order 1 constraints, or no constraint from current large-scale structure. Really, you can't constrain alphas anymore. You have to throw them out and instead constrain these objects that sit in the Lagrangian. And hopefully I've convinced you we've started work on how to do that, using data from upcoming surveys. And this is the kind of pub quiz, name that telescope. I won't keep you guessing. That's Vera Rubin, that's Desi, and that's Euclid. Okay, that's essentially takes me to the end of what I wanted to say today. Very quick visual conclusions. We looked at this idea of parameterizing a whole space of theories. We understood how the binary neutron star merger constrains alpha T, and we met the dark sirens method for constraining alpha N. We then jumped into large-scale structure, understanding that it was the nonlinear regime we really wanted to target, and I introduced you to this suite of simulations which hopefully will enable us to constrain the appropriate objects in that regime. And I'll leave it there. Thank you.
I was wondering, this alpha m, as you said, as you showed, it's always a simple question, is constrained through an integral constraint. The constraint is actually an integral constraint. So if it actually has, if it's not monotonically set, but if it has some very fast oscillations instead, it can easily be zero. The constraint can be zero without the alpha m being zero. Whereas thinking of fast oscillation in alpha m just ridiculous. You're almost only considering against monotonic changes with set or something. Or how? How's that?
Right, so you're absolutely right that if we did have an alpha m that was oscillating really fast around 0, we wouldn't be able to detect it, basically, unless we had amazing gravitational wave data at every single redshift. So yes, that's true, and so we are kind of assuming here monotonic smooth functions. That is motivated by most of the kind of mainstream dark energy models. They're not generally producing very fast oscillations in redshift. Maybe some are, but the kinds of mainstream theories do have a smooth limits. I'll comment on that.
Concerning the constraints on this parameter, alpha n, the running of the compass, I think that there is a fundamental limitation in the constraint, which is due to the lensing, the gravitational lensing of the gravitational waves by the large-scale structure at high redshift, or even by possible strong lensing of the gravitational wave, which would mimic deviation from GR, right?
Yes, very good. So I didn't talk about gravitational lensing of gravitational waves today. I just showed a propagation equation for FRW. You're absolutely right that really they're propagating through potential wells. So that is something we have to think about. We're not worried about it with the current data because the errors on the luminosity distances from gravitational waves are vastly bigger right now than the effect of lensing. But yes, in a future where we have much better polarization data, we'll get much better handles on the the luminosity distances, and then it will be a systematic inlet. Whether we can model it, maybe there is a way you can use observations of large-scale structure along that particular line of sight to try and estimate it, but there may be some kind of limit.
Thank you. Thank you very much. I think if you go to your summary slide, yes, example here, one technical question. Why is that? Couldn't you remove the G5 by defining the new metric, hence remove this extra freedom?
Oh, right, so G4?
Yes, just that the measure going on different measure.
Exactly. I mean, yes, you could do that, and then but
without
then
changing any of the dynamics here. Yeah.
but you would then have to, well, you'd have to take account that your matter is moving on a different metric. So I mean, yes, this is a Jordan frame formulation, I guess, but we find that the most convenient to work out.
The metric. But what I meant is, does your code, can your code handle that kind of metric? Do you have a parallel version of your code?
An
Do you like
Einstein
to develop
version.
one?
We do not right now, so it's certainly been enough work trying to get this version working. And maybe it's a possibility. I guess that would just imply some pretty weird dynamics for the forces between particles.
It's not difficult if you were just doing that measure. You just get a this.
Yeah. I think it's possible.
Because the nice thing is you can now have, they can interact with more scalar field, then the way you write it.
They can interact with more scalar fields.
Yeah, increase.
You mean you can have a more complicated
Well,
form?
yeah, if people want to explore complicated ones where this is more restrictive.
We aim to serve the community, so if people say they really would like an Einstein frame version, then we could consider it, yes, which haven't done so far.
One just scientific comment. Why is alpha m so, why alpha m could be so big? It's not, most cosmology says that better than 1% can be constrained. How come this number is so arbitrary? Why is this number so much?
Why is it
Intuition.
Okay, maybe I was going to slightly twist your question a little bit, but perhaps a way of rephrasing that is, why is the constraint on alpha t so small? Right, because all the others are constrained to order unity at the moment. And the reason the constraint on alpha t is so small, that constraint comes basically from the scale of 2 seconds relative to the propagation time of gravitational wave of that system, which is 130 million years. So that's why that's so small, is perhaps you're seeing that alpha m is large relative to that. Today I did talk about primarily the gravitational wave constraints on alpha m. There are some other constraints from, I think there is a bound on it at high redshift from Big Bang nuclear synthesis, I think, if you have an involving G. Yeah.
But also from the Ockmore, there are constraints on the variable G, aren't they, from the natural area. We apply
From, sorry?
from Ockmore,
But this is cosmological. Good. So, sorry, I've thought a little bit. Of course, the answer to your question is your intuition that G is really well constrained comes from small scales. It comes from laboratory tests, it comes from solar system tests, etc. This is only describing cosmological changes to G. And on those scales, the constraints on variations of G are about 30%. It's much, much weaker.
Well, somewhere I missed it. This is a little bit like Dirac very gravitational constant, looking at the slope of that. I thought that number must be fairly well constrained, but here you're saying is
because it's very poorly constrained in cosmology. Just using positions of galaxies or gravitational wave data.
Thank you.
it is so if you have another family of modifying electromagnetic effect or by methods, then you have to start all over again.
Lots of work.
Yes and no. So you have to start all over again. You get more alpha parameters, the more complicated you make your theory. Some of them will be the same. So you'll get all these 4. So you can use your constraints on those, but you'll get, I think it's another 3 in the case of a vector tensor theory. And if you have a, Tevez style theory, then you've got about 14. That's,
Magnetic in the sense that you actually have 2 methods, not what Einstein thinks.
that case is done in one of the papers I referred to earlier. I can't remember how many parameters it is, but sort of, it's more than 10, I think.
Could you turn the questioner's microphone on? It's not actually switched on at the moment.
Thanks for the nice talk, Tessa. So I'm wondering about the alpha t constraint. So it seems, if I understand correctly, that that's solely using the time of flight difference to the source. But is there not also a Shapiro time delay that could be different between light and gravitational waves? And therefore, if that depends on, in some other way, on the alpha parameters, you would actually have a constraint on some combination of those, if they could cancel each other out, rather than simply alpha t from the time of flight. Does that make sense?
In my mind, those 2 things are 2 sides of the same coin. So if gravitational waves and photons couple to different metrics, and therefore experience potential wells, and therefore experience the Shapiro time delay in a different way, you'll get a bigger difference.
But the Shapiro time delay depends on the potential along the line of sight, whereas
So,
simply the time of flight depends only on the distance to the source.
Yes, there is a constraint on the Shapiro time delay, which has been published, which is about 10 to the -7 between gravitational wave and electromagnetic wave.
yeah.
But this assumes that we know what is the dark matter along the line of sight, or dark matter or ordinary matter, and notably the dark matter is the halo of dark matter of the host galaxy and our own Milky Way galaxy.
Right, yes.
And
Yeah.
this is due only to the difference of time of arrival.
Yes.
But 10 to the -7 is much weaker than 10 to the -14. So why does that not impact the alpha t constraint?
Because you make the test with the formula for the Shapiro delay. So you measure the parameter in the Shapiro time delay, which is the gamma parameter, which is in front of the factor which involves the mass of there is a log. And so this gives you the difference between the 10 to the -7 and 10 to the -15.
But also probably, I mean, if you have 2 effects, you have to be very fine-tuned to get a very small number. So it's probably a constraint on both effects. And any more questions? Tessa? Okay, if not, yes.
May I just for clarification, the braiding you were talking about, is the braiding parameter the G4 parameter?
No. So braiding parameter is alpha b, which is related to combinations of G3, K, and G4. So it's not quite a one-to-one mapping.
As well. Oh yes, G3 as well. I see it. Yes, G3. Okay. What about the alpha K? Isn't that just a K? There's nothing else.
No, you would think it would be, but it's not. So the alphas are basically
G3 term.
like algebraic combinations of those 3 and their derivatives.
No, I understand. Thank you.
And so we turn to our next speaker, Arthur Russell.